All right, sections 4.3 and 4.4. I went ahead and combined those into one lecture, both dealing with the definite integral and applications. Now, in the previous section, we talked about the indefinite integral, right? And essentially, the indefinite integral came from finding the antiderivative of a function. We were looking for the area under the curve. We talked about that sum notation, right, the Riemann sum notation, and how we could put use rectangles under our graph to approximate the area, that kind of thing. But all of that eventually led us to the indefinite integral, that integral of f of x dx. Right? But the concept was we're calculating the area under the curve. Now, in the previous section, we were able to do a couple of those areas or calculate a couple of those areas because we had shapes that we knew the formula for finding the area of. We did a couple of examples with triangles, so we could use the area of a triangle, recognizing the shape under the graph. We also looked at a case where we had a constant function. The graph was a horizontal line. And so the area under the graph ended up being just a rectangle. And we could use the area of the rectangle to give us the area under the curve. But of course, that's only going to work as long as you have a region whose, first of all, the shape you can recognize. Secondly, you know the formula for calculating the area of that particular shape, right? So what happens if that's not the case? Because, of course, most curves are not going to give us nice regular shapes under the grass, like triangles or rectangles or what have you. So just to remind you of how that kind of went. So I'm looking at this first example. I'm finding the area under the curve of the graph of y equals square root of 4 minus x squared. And if you graph that function, you would see that this is a curve that intersects the x-axis at negative 2 and 2. It also intersects the y-axis at 2. So recognizing that that is really just half of a circle whose radius is 2. And by recognizing that, well, I can give you then the area of that region. I can use the area of a circle, which is pi r squared, and I just need half of that area for our circle. And in this case, the radius is 2, so it's 1/2 pi times 2 squared, or 4 pi times a half, or 2 pi. And that gives me the area under that region. But again, it was all based upon the fact that, hey, that I recognize that as half of a circle, and I could use the area formula for a circle to calculate that area. Right, so the geometry works well as long as you have that. Now, the definite integral. All right, so this is what I mentioned at the end of section 4.2. So with the indefinite integral, we did not have the a and the b. We did not have the limits of integration. We were simply looking at the integral of f of x dx. We said ultimately that does represent the area under that curve. But all we were able to come up with was, we knew that we had to calculate or find the antiderivative, right? And then we always had to tack on that plus c, right? Because we were talking about general antiderivatives. But we did make the observation that if you, I'm just going to put a little X through this for a second. If you ignore that limit statement, then that sum notation, it was the Riemann sum, we called it, the sum notation, or sigma notation, is what we use to approximate the area under the graph. Right? So we said, look at the sum as I goes from 1 to n of f of x of I delta x. And then we picked the n value. We said, okay, let's pick the number of subintervals. We used rectangles. Right? How many rectangles do we want under the graph? And then we would calculate the area of each rectangle, add the areas, and get an approximation for the area under that curve. Now, we finished up that previous section, though, by noting that, hey, the best approximation would come from, or better approximations, we'll say that way, comes from using more and more rectangles. Because the more rectangles you put under the curve, the smaller the rectangles become, the better they approximate the area under the curve. And we said, theoretically, I'd like as many rectangles as I can get, so let's just let n approach infinity. And if I end up with an infinite number of rectangles, theoretically speaking, of course, then we could calculate the area under that curve exactly by summing up the areas of these infinite numbers of rectangles. Right? So that's where this notation came from. Right? So of course, we don't want to have to use that sum notation. Obviously, you can't add an infinite number of rectangles. Well, that's a topic for another day. So if you're heading into calculus, if you're going to take some calculus, the more rigorous calculus, we get into more of a discussion of that type of thing and actually talk about adding infinite numbers of values. Right? But in this case, we're theoretically, right, we have an infinite number of rectangles. I can't add up the areas of those rectangles because I keep having more and more rectangles. Right? So the Riemann sum is not going to work for us. I can't just add a bunch of rectangles. We need a better way. We need a way to calculate the area under that curve without having to go through all that. So if I don't have a geometric formula like we did in the previous example, and I want to be specific and not just approximate like we do with the Riemann sum, we come up with a formula for calculating the area under the curve, which is used or comes from using this definite integral. Right? So the fundamental theorem of calculus, and I'll spare you all the song and dance as far as why this works the way that it works and all that. We'll just put it into use. The integral from a to b. Watch my language and notation here. The integral from a to b of f of x dx, where a and b we call the upper and lower limits. A is your lower limit, b is your upper limit. So we're talking about the area under the curve from x equals a to x equals b. This can be found by finding your antiderivative. There's our notation we used in the previous sections. If little f is our integrand, its antiderivative is cap f, and we evaluate the antiderivative cap f at those limits, a and b. Or in other words, I'll take cap f evaluated at the upper limit b minus cap f evaluated at the lower limit a, where again f cap f is the antiderivative of little f, so that makes cap f prime little f. Right? So again, we're evaluating an integral, so we are going to find the antiderivative of our integrand. In the case of the indefinite integral, remember we said that was really just a function where we tacked on the plus c, and then if we knew certain information about our antiderivative, we could actually find the c value and give you the exact antiderivative, but it's still a function. All right, so it's still f of x plus c whether or not we can find the c value or not. That's what the indefinite integral calculates. Right? The definite integral, though, once you put those limits of integration, the a and the b value, now I'm able to actually calculate the area under that curve as a fixed value. Right? So once I know my starting point and stopping point for the graph, then I have a region that has boundaries all the way around it, and I can calculate the area. And that's what the definite integral is used for. Right? But all this integral notation it comes from the use of this notation. And so ultimately, eventually I'll tell you why that integral symbol is what it is. That big long S that we use for the integral, it's an elongated S which represents the limit of sums. And that's why we use that big S to represent the integral. But that's where that comes from. Right? And so ultimately then we're able to use this definite integral to find the exact area under our curve from a to b. Now do be careful, watch again the calculation. So I have my antiderivative evaluated from a to b. You're always going to first plug in your upper limit minus plug in your lower limit into your antiderivative. And here I just have a few different examples. Right? So there's really nothing new or different in terms of finding the antiderivative. That hasn't changed. It's just now we're able to actually evaluate it and plug values in and come up with a number instead of just a function or family of functions. So for example, I'm going to say evaluate the integral, or in other words, we're finding the area under the curve on the given interval. All right, so all that means the same thing. So here's like number one, I have the equation y equals 5. Now remember, recognize that's just a constant function whose graph would be a horizontal line. So that would be a case where actually we could calculate the area using just the area of a rectangle formula. But we're going to put it in the context of our integral now. So our function, our equation, our curve is y equals 5. And we're interested in the area under that curve on the interval from 1 to 3. All right, so find the area under the curve, evaluate the integral, means exactly the same thing. So we set up our integral from 1 to 3 of 5 dx, because I'm going to use x as my variable. So we have our antiderivative of 5, remember, which would be 5x. Now, notice that when we did indefinite integrals, right, if I just had the integral of 5 dx, when we found the antiderivative, we would say 5x plus c. Notice I'm not putting the plus c here. We'll look at that in just a second as far as why I don't need that. But watch my notation again here, though. I'm finding the antiderivative, which is 5x, and then we're going to evaluate 5x from 1 to 3. So we plug in that upper limit first in place of x, so 5 times 3, minus, plug in the lower limit, 5 times 1. And I've got 15 minus 5, or 10, as the area under that curve. Call it 10 square units if you wish. Now again, notice there's no plus c when I did the antiderivative. Why do I not need the plus c? Why don't I put that as we did before? Well, let's look at what happens if we do. So here's the same integral. Here's our integral from 1 to 3 of 5 dx. If I included the plus c when I did my antiderivative, right? So it's 5x plus c, and it's still evaluated from 1 to 3, right? Because I'm on the integral from 1 to 3. So we plug in the upper limit, which is 3. I've got 5 times 3 plus c. Minus, we plug in the lower limit. I've got 5 times 1 plus c. But then notice what happens when you distribute this negative through the parentheses, the second half of this thing. You get 15 plus c minus 5 minus c. And so those c's end up subtracting out. Now remember, the c represents an arbitrary constant. But when I'm talking about a specific antiderivative, it would have to be the same constant in both cases. So, I mean, it's not that we're looking at plus c and minus c, and c will cancel out. The c's have to be the same number if you're representing the same antiderivative. But regardless, all right, you end up with the addition and subtraction of that same constant. They're always going to knock each other out of the calculation, right? So technically, should we put the plus c when we do the antiderivative? Sure. But in the case of a definite integral, I don't need it because it's always going to subtract out. So I end up with 15 minus 5 again, or 10, which is what we got previously. All right. So, we don't bother putting it. It just saves us a little bit of work, right? Not a whole lot, but a little bit. All right, now just again, a couple of other examples, just to remind you of how to do some antiderivatives and maybe again a couple of other things to be aware of. So number 2, our curve is y equals x squared. We're interested in the area under the curve of y equals x squared on the interval from 0 to 3. So I set up my integral from 0 to 3 of our function x squared dx. Our antiderivative, right, power rule, x cubed over 3. And we're going to evaluate that from 0 to 3. And again, you always plug in the upper limit first. So I've got 3 cubed over 3 minus, plug in the lower limit, which is z cubed over 3. And then you're doing your calculation, right? So 3 cubed is 27 over 3 is 9 minus 0 or 9. And there's our area. Number 3, I've got the equation, I've got the graph of y equals 1 minus x squared evaluated or over the interval from negative 1 to 1. All right, so again, there's our integral, negative 1 to 1, lower limit to upper limit. Notice we're always moving from left to right along our interval of our function 1 minus x squared dx. Find our antiderivative. The antiderivative of 1 is x. Our antiderivative of x squared, again is x cubed over 3. And then we're evaluating from negative 1 to 1. So plug in 1, always plug in the upper limit first, minus, plug in this lower limit, and then from there it's just calculations. I mean, that's really all that is. And then we end up with 4/3. For number 4, I've got y equals e to the x. Again, just different functions, just giving you some examples. So here's our equation, here's our curve, and I'm interested in the area under the curve y equals e to the x on the interval from 0 to 3. So here's my integral from 0 to 3 of e to the x dx. Now we're doing antiderivative, right? So the antiderivative of e to the x, remember, is still e to the x. And then we're evaluating that antiderivative from 0 to 3. We plug in our upper limit, and I've got e cubed minus our lower limit, e to the 0. Now, I just left e cubed as e cubed. E to the 0, remember that's a non-zero constant raised to the 0 power, always gives you 1. So I get e cubed equals 1. That's the exact value of this integral. And that's typically what you are asked to find. If you're just finding evaluating an integral, you want the exact value. So notice I'm not approximating anything here. I'm not approximating e cubed or anything. So as usual, My Math Lab, watch your question. If they want the exact value, that's the exact value. If we want to approximate it, then we could plug that into the calculator and approximate it to however many decimal places we wanted. Number 5, I've got y equals 2 over x as my curve, and we want the area under that curve on the interval from 1 to 4. So here's our integral from 1 to 4 of our function 2 over x dx. And I rewrote this one just to remind you about that constant rule for integrals that, I could rewrite 2 over x as 2 times 1 over x, and then you can always pull that constant factor out of the integral if you wish. That was a constant multiple rule that we had for integrals. So I rewrote this one as 2 times the integral from 1 to 4 of 1 over x. And, whether or not you do that, that's again, one of those things that's purely up to you. It's just personal preference. If you find it less confusing to go ahead and pull the constant out and then just work with the simpler function, and if you can do it by leaving the 2 in there, that's fine as well. But either way, you end up with 2 times the antiderivative of 1 over x. Remember, our antiderivative of 1 over x is natural log of the absolute value of x. So I've got 2 times that evaluated on the interval from 1 to 4. And again, we plug in our upper limit. Now notice in this case, since I pulled that 2 out as a separate factor, and again, you could do this either way, I just went ahead and did 2 times natural log of 4 minus natural log of 1, right? Natural log of the upper limit minus natural log of the lower limit. You could just as easily rewrite that as 2 times natural log of 4 minus 2 times natural log of 1. I mean, that's just a matter of which way you care to write it. But either way, natural log of 1 is 0. So I've got 2 times natural log of 4 minus 0, which leaves me with 2ln of 4. Now, that's a perfectly good answer. 2 times natural log of 4, 2ln of 4. I also rewrote it just to remind you of one of your properties of logs. Remember, if you have a constant multiple in front of a log, you can put that into the exponent of your argument. So 2ln of 4 is equivalent to the natural log of 4 squared, just bringing the 2 into the exponent. So I could then write that as natural log of 16. Right? But again, either way is fine. 2ln of 4, natural log of 16, either one of those is acceptable as values for that integral. But again, notice I'm giving it as an exact value. I didn't approximate that. You only approximate if you're asked to, which typically only happens when you're dealing with applications. Number 6, just throw in one more of these. So again, remind you of some of these antiderivatives. So I've got y equals 2x plus 1 over x squared on the interval from 1 to 4. So I've got the integral from 1 to 4 of 2x plus 1 over x squared dx. Our antiderivative of 2x, power rule, 2x squared over 2, minus, now the antiderivative of 1 over x squared. I didn't work it out. You should be able to do that. I've got 1 over x squared, which is x to the negative 2. Our antiderivative would be x to the negative 1 over negative 1, right? You increase the exponent, divide by the new exponent. So that would give me a negative 1 over x, so that plus becomes a minus. And there's our antiderivative of 1 over x squared, which is negative 1 over x. Right? But again, that's old business. That's just power rule, finding the antiderivative of 1 over x squared. And then we're evaluating from 1 to 4. Right? And I just went ahead and simplified. 2x squared over 2, of course, is just going to give me x squared minus 1 over x, evaluated from 4 to 1. So I went ahead and plugged in the 4, plugged in the 1. Again, that's from that point forward, it's just calculations. Just make sure you're always plugging in the upper limit first, minus the lower limit. So I got 16 minus 1/4, and then 1 minus 1 there, which is 0. So that would leave us with 15 3/4, or 63 over 4. Right? And it goes, as always, whether you give it as a fraction or mixed number, that's just a matter of preference or what's asked for in your directions. Applications of the definite integral. Here's something a little bit different. Um, new topic, but again, it's really not going to add much to our discussion, but it is an example of an application with the integral, the definite integral. Finding the average value of a function. Right. So, we're talking about finding the area under the curve from A to B, from point A to point B. We could also use this in the context of finding the average value of a function over an interval. So we're going to let f of x be a continuous function. Remember that idea of continuity? Continuous means you could draw the graph by putting your pencil to paper and not picking it up till you're done. So f has to be continuous on our interval from A to B, whatever that happens to be. Then the average value of our function, which we're going to call y sub average or f sub average, whatever your function name is, it's the average value of your function over that interval from A to B, is given by 1 over b minus a times the integral from A to B of f of x dx. All right. So it's simply adding in, or I'll say adding in, multiplying your integral by 1 over b minus a. And that would give you the average value of your function over that interval. And again, I'll spare you the song and dance as far as where that formula comes from or why it works the way that it does. We're just going to put it into practice. That's all we need it for. So for example, I've got a company that determines that its weekly online sales, S of T, S for sales in this case, in hundreds of dollars, watch our units here, T weeks after online, get this, T weeks after online sales begin, can be estimated by the function S of T equals e to the T. All right, so that's our weekly sales, T weeks after sales have begun, and that's in hundreds of dollars. We're asked to find the average weekly sales for the first 8 weeks of our after online sales have begun. All right. So of course there's our trigger. I'm looking for the average weekly sales. So I could calculate the integral of our function over the time period. In this case, it's the first 8 weeks. So we're going from t equals 0 to t equals 8. And that, of course, could be anything. So just watch your wording in your problem in terms of, am I interested in a specific interval of time? What is my starting point? What is my stopping point? And so here, I'm interested in the first 8 weeks, so I'm going from 0 to 8. And since we want the average number of sales, or average amount of sales per week, we're multiplying our integral by 1 over b minus a. And so our upper limit here would be 8, our lower limit would be 0, so it's 1 over 8 minus 0 times our integral from 0 to 8 of e of t, e to the t dt. Right? So that would just give us 1/8 times our antiderivative of e to the t, which is still just e to the t, evaluated from 0 to 8. Right? That's the integral part. So then I've got 1/8 times e to the 8th minus e to the 0. And there's the 1/8, that's our 1 over b minus a. And then there's our e evaluated at the upper limit of 8 minus e evaluated at the lower limit of 0. Now again, e to the 0 is 1. So I've got 1/8 times e to the 8th minus 1. 1/8 e to the 8th minus 1/8. Distributing the 1/8. Now in this case, I went ahead and approximated that because this is an application. We said that's typically where you're going to approximate. You want to answer a question. Our question was to determine the average sales, average weekly sales over the first 8 weeks, right, after the sales began. So I want to give that as a reasonable, usable value. So I went ahead and approximated that value. I got 372.49. Now that's in hundreds of dollars per week, right, or your average sales. So I went ahead and converted that to a more useful value. Since that's 372.4900, went ahead and knocked that decimal over a couple of places, and I've got $37,249. So that would be our average weekly sales. I should put there per week as our unit, because that again is the average sales over that time span over the first 8 weeks. Okay, so it just adds a little bit extra to it. It's another little concept. We can put some application to the use of this definite integral. Now, the definite integral, as we talked about so far in terms of finding area under the curve or area under the graph of a function. Now, when we talked a little bit about this in the previous section, when I talk about area under that curve, there's a couple of things to consider there. It's the area between the graph of our curve and the x-axis, right? So that's what we mean by the area under the graph or area under that curve. We also, in the last section, talked about the idea of net area, right? Because we've had a couple of graphs where part of the graph was above the x-axis and part of the graph was below the x-axis. And we said, if we're talking area under the curve, area between our graph and the x-axis, area above the x-axis is considered positive area, area below the x-axis is considered negative area. And so the integral from a to b, our definite integral, represented what we called the net area from a to b. So I would take whatever positive area we had, subtract out whatever negative area we had, and we came up with net area. All right, so that doesn't change. I mean, the idea of what the integral measures, it's the area under the graph of your curve between the graph and the x-axis, taking into account both positive or negative area. Well, here's the next logical step in that. All right, so we have our definite integral, area between the graph of our function and the x-axis. All right, net area specifically. What if we wanted to calculate the area between two different functions? All right, so instead of just our function and the x-axis, how about if I have two functions and I want to find the area between the graphs of those two functions? Okay. Terminology, notation, again, be careful here. I'm looking at the area of the graph, or between the graphs, of these two functions, y equals f of x and y equals g of x, on our interval from a to b. So again, we'd set up our integral, because that's to calculate the area from a to b, from lower to upper limit, left to right. And I think this reasonably makes sense. If I want to find the area between two curves, we find the area under the upper curve, right? Whichever, if you graph the two functions, one of the graphs is going to be above the other graph. So if I calculate the area under the graph that's on top, and I calculate the area under the graph that's on the bottom, and I take the difference between those, then that's going to leave me with the area between the two. All right. So it's kind of like this idea. A quick reference over here. Let's say I've got two functions. Let's say here's our function f and here's our function g. All right. If I calculate the area under g, that's all of this. If I calculate the area under f, that's all of this. All right. And if I subtract out the area that's under g, then what I'm left with is the area between the two. All right. That's the idea. I think that's a pretty reasonable observation to make. Right? Now, that's going to be true as long as f is always above g. All right. So, of course, I want to take the function that's on top. I call it the upper function. And I want to subtract out the area that's under the graph of the function that's on the bottom. I call that the lower function. And the difference between the two would leave me with the area between the two curves. Now, again, that's going to be true as long as f is greater than or equal to g. As long as f is above g, then I could find the area by integrating from a to b, f of x minus g of x. It's always just the upper curve minus the lower curve, provided f of x is greater than g of x in the interval. Of course, if g is going to be the graph on top, then I would look at the integral from a to b of g minus f. Right? So it's always just with respect to which one is the upper and which one is the lower function. Right? So when g of x is greater than f of x. Now, we also have here where f of a equals g of a and f of b equals g of b. That is referring to, if I just said, hey, find the area between these two graphs, and that was all I asked you for. we would look for points of intersection between the two graphs so that we would have boundary points to actually find the area of. So in other words, if, like the one I just sketched up there, I wouldn't be able to find that area because it would end up being infinite, right? Those are just two horizontal lines. But what we're looking at is something like in the form like this. Maybe one of my graphs looks like this and the other one looks like that. And so here's the area between those two curves, but I would have to know what these 2 points of intersection are, so those would serve as my boundaries, right? So in other words, that's our upper and lower limits, right? So, and I have all that kind of illustrated out a little more detail as we go through, but I felt it was maybe a little relevant here during this discussion, so I'm going to throw that in for now. But that's why we have this f of a equals g of a, f of b equals g of b. That's simply asking us to find the points of intersection, right? Where are the boundaries for the region whose area you're actually trying to find? So in other words, like I said, it's a pretty straightforward idea. Otherwise, we're finding the area as the integral from a to b of the upper curve or upper function minus the lower function, all right? Given that the graphs intersect at the points where x equals a and x equals b. Now, what happens though if in my interval that changes, right? So let's say f of x is greater than g of x for part of our interval, and then they changed position, and g becomes the upper function above f in another part of the interval. All right, then how do we calculate the area there? Well, again, you have to be careful, because if I want the total area enclosed between those two graphs, then I'm going to have to split that into two separate intervals. And so I would split it wherever that point of intersection is in my graph that I have below, at that point B, where those two graphs intersect. So if you look at the interval from A to B, over that interval, f is the upper function and g is the lower function. But then they cross each other, and over the interval from B to C, g becomes the upper function and f is the lower function. Right? So if we're calculating total area, then we need to break the interval at whatever point they intersect. I think you're only going to have like maybe one of those in your homework, so it's not a very good. But at this point where they intersect and they change orientation. So we would have to split the integral and say, okay, let's find the interval from A to C all the way across to calculate the area between the two curves. I'm going to have to calculate the area from A to B where f is on top and g is on bottom, so I'm using f minus g. Then I'll add the integral from B to C where g is on top, so I would use g minus f. Okay. Now, if you didn't do that, if all you did was the interval from A to C of f of x minus g of x, then we're back to the idea of net area. And it would give you the net area taking into account wherever f was above g, that would be positive area, and whatever g was above f, that would be considered negative area. Okay? So we don't want to get into that. We're interested here in the total area enclosed between the two curves. So if they happen to intersect and the orientation changes as far as which one's on top and which one's on bottom, we simply then reverse those within each of the intervals. Okay? But like I said, I think you have maybe one of those in your homework. The rest of them are all going to be more straightforward in terms of just find the area enclosed between the two curves, find your points of intersection so you know your limits of integration. If you can look at the graph and tell what those points of intersection are, great. If not, then you're going to have to find those points of intersection. Well, how do we find that? We'll set the two functions equal to each other. I mean, where are they going to have points in common? Wherever the two functions are equal. So you set the functions equal to each other, solve that for x, and that would give you the boundaries. That would give you your x coordinates of your points where those two graphs intersect. And that would then be your limits of integration. So for example, finding the area bounded by the graphs of y equals 3x minus 1, nice little linear function, and y equals x squared minus 1, nice little parabola. So I went ahead and graphed those two, because you do need, of course, to know which one is on top and which one's on bottom. And if you can tell that, without graphing it, then great. But you do have to have that orientation, because otherwise, if you do the calculation and your functions are reversed as far as upper and lower, you're going to get the same value, but you'll end up with a negative value, right? And here we're talking total area, and total area is always positive. So I need to know who's on top, who's on bottom, so that I know which direction to set up the subtraction in my integrand. So there's the graph of the two functions. So from the graph, I can see that y equals 3x minus 1 is the upper function. It's above the graph of y equals x squared minus 1 over this portion of the interval where they actually enclose the region, right? Because notice, once you go outside of that, like if you look at this region over here, then x squared minus 1 is above 3x minus 1 over there, right? But I'm not interested in that region. I'm only interested in the part that's actually enclosed between our two functions, right, which is the shaded region that I have. So over that interval, 3x minus 1 is the upper function, x squared minus 1 is the lower function. I need to know the points of intersection so I can set my boundaries. So notice I went ahead and set the functions equal to each other. 3x minus 1 equals x squared minus 1, and I just solved that equation for x. So it leads us to a nice little quadratic, which actually is factorable. And we get x equals 0 and x equals 3. So there are our points of intersection, so that I'm looking for the area bounded by those two curves over the interval from 0 to 3. Now, once we have that, we're back to business as usual. We're just going to set up our integral. So here's our area, integral from 0 to 3 of the upper function minus the lower function. So 3x minus 1 minus x squared minus 1. Now, as always, watch your basic algebra. I need to distribute the negative through that second function. So I've got 3x minus 1 minus x squared plus 1. This is all simplifying the integrand initially. So the ones will subtract out. I'm left with 3x minus x squared. So I've got the integral from 0 to 3 of 3x minus x squared. Find our antiderivative, 3x squared over 2 minus x cubed over 3. Evaluated from 0 to 3. So plug in 3. Plug in 0, upper limit minus lower limit, and I ended up with 135 over 6, or 22.5. And that's the area between those two curves. Basically, we'd say it's the area of that shaded region. Right? But I can give you a second one, just to give you another example. Again, some different types of functions. So here, finding the area bounded by the curve y equals 4 minus x squared. And again, that's a nice quadratic parabola facing down. And y equals 3. There's our horizontal line again. Y equals a constant. Right? So there's the graph. I have a shaded region here, which is the region bounded between those two curves. And we needed our points of intersection. So again, I set those equal to each other. 4 minus x squared equals 3. Subtracting 4, I've got negative x squared equals negative 1, or dividing by negative 1. X squared equals 1, so x would be positive or negative 1. So that gives us our limits of integration. I've got the area between those two curves. That shaded region then is the integral from negative 1 to 1 of the upper curve minus the lower curve. Right? So 4 minus x squared is on top, and then the horizontal line y equals 3 is on the bottom for that shaded region. So upper minus lower, 4 minus x squared minus 3, or 1 minus x squared, integral from negative 1 to 1. Antiderivative of 1 is x. Antiderivative of x squared is x cubed over 3. And again, we're evaluating from negative 1 to 1, our limits of integration. And so then I'm plugging in 1, our upper limit, minus, plugging in negative 1, our lower limit. And from there, it's just straight calculations. And we end up with a total of 4/3. And so, again, context, we would say 4/3 square units, because that is the area that we're talking about. It's the area between those two curves. Right? So that tends to go pretty well. I think that's a pretty straightforward idea. Main thing I said, just be careful. Make sure you're always plugging in your upper limit first, and then your lower limit when you're evaluating a definite integral. And then when you're finding the area between two curves, make sure you're clear as far as which is the upper and which is the lower. Right? And that is it for those sections 4.3 and 4.4.